Inverse functions example 1. Find the inverse of f of x equals to 2x. What we're going to do is we're going to draw the graph of this linear function f of x equals to 2x. To draw the graph, I need a few of the coordinates of the graph. I know it's a very easy graph to draw, but I'm going to use the coordinates to find the inverse of f of x equals to 2x. So let's find the coordinates of these points in the table. We see that when x is negative 3, we substitute negative 3 into f of x. We have 2 times negative 3 gives you negative 6. And so we continue in this way, and we have the coordinates when x is 1, y is 2, and when x is 2, y is 4. Let's plot these points on the Cartesian plane. So we have a coordinate at negative 3, negative 6. We have another one at negative 2, negative 4. Our third point is negative 1, negative 2, 0, 0. X is 1, y is 2, x is 2, y is 4. And we have another point, or the last point can be when x is 3, y is 6. Let's draw the graph. So this is the graph of f of x equals to 2x. I'm going to label a few of the points. One of the points is when x is 2, y is 4. Another one when x is 1, y is 2. I have a point at 0, 0. And the last point that I'm going to label is x is negative 2, y is negative 4. Now we're going to take these points and we're going to reflect each of these points in the line y equals to x. So the next step is to draw the graph y equals to x. The graph is the pink graph, so we have y equals to x. Now we're going to take a certain number of coordinates and we're going to reflect them in the line y equals to x. To reflect them in the line y equals to x, we're going to draw a pathway perpendicular to the line y equals to x. Let's start with a point x is 2, y is 4. So if I draw a pathway from x is 2, y is 4 perpendicular to the line y equals to x, I see that the image of the point when x is 2, y is 4 is at when x is 4, y will be 2. Let's repeat this process for one other point. So I'm going to draw a pathway, say from x is 1, y is 2, perpendicular to the line y equals to x. And I see that the image of the point when x is 1, y is 2 now lies when x is 2, y is 1. The origin is on my axis of symmetry, y equals to x, or my line of reflection, and so its image will also lie on the line of reflection. We're going to do it for one more point, so we're going to reflect the point x is negative 2, y is negative 4. And so if we draw a pathway perpendicular to the line y equals to x, we see that the image of x equals to negative 2 and y equals to negative 4 now lies at x equals to negative 4 and y is negative 2. So let's join the green dots. So when I join the points of the inverses, sorry, not the inverses, the images, I get the inverse of f of x, and that is the black line that you see. We're now going to find the equation of this black line, and we're going to do it algebraically. So we start by saying f of x equals to 2x. We're going to rewrite it in the format as y equals to 2x. You notice that when I had the point 2, 4, and I reflected it in the line y equals to x, its image had the coordinate 4, 2. So you see that the x and the y coordinate each time of the image swapped positions. I'm going to do the same with the variables. I'm going to replace the y variable with x, and I'm going to replace the x variable with y. So I've interchanged the variables. And now I write it in standard form, and I see that y equals to half of x. So the equation of the black line is y equals to half of x, and we say that y equals to half of x is the inverse of f of x equals to 2x. Now, my graph was given to me using functional notation, so I'm going to write the inverse using functional notation. And so the inverse of f of x is a half of x. So be careful with this notation. The notation for the inverse is not an exponent. This is not an exponent. So you can't say that it equals to 1 over f of x. Also, we may only use this notation if we know that the inverse is a function. And I'm going to explain this concept to you in a while. But I just want to draw your eye to the graph. Do you notice that my graph f of x equals to 2x and the inverse function all intersect at 0, 0. So this is the common point on the line y equals to x. I call the line y equals to 2x, or f of x equals to 2x, a function. And how do we know it's a function? We're going to conduct what is called a vertical line test. So we take a vertical line and we sweep it across the Cartesian plane. And each time you would notice that this vertical line cuts f of x at one point only. And if I continue sweeping it, can you see that this vertical line cuts the inverse, which is half of x, at one point only? So if a vertical line cuts my graph at one point only, then my graph is a function. So in this situation, f of x is a function and its inverse is also a function. There is another test that we can conduct. The second test is called the horizontal line test. So I take a horizontal line and I slide it up and down my Cartesian plane. And we check and we see that this horizontal line is cutting f of x at one point only. We say that f of x is a one-to-one function. And if you notice, it cuts my inverse at one point only. So any graph that is a one-to-one function will always have an inverse that is a function. So just to recap, my linear function f of x equals to 2x is what I called a one-to-one function. And so because it is a function, it has an inverse. And I see that my inverse is also a function.